So we are studying gravitational field. So we understood what is a field. Field is space. Field means space. And how to define a space? We define space using spatial coordinates. Spatial coordinates means space. So Cartesian system, cylindrical system, you can have spherical system. Those are spatial coordinates. So spatial coordinates helps you to define the space and then the field. Now, example, in math, we define functions like this, f of x, that is x squared plus 1. You can see this is a equation defined in spatial coordinates. So this is a field equation, right? So this is a field equation. Now, if you look into this one, fr is equal to 1 divided by r squared. So you can see r is distance. Distance is space, right? Space coordinate. So that r radius or distance, you can say, that is coming with cylindrical coordinate system, polar coordinate system. Those who are doing specialist math, polar system. Polar system, r theta cis, r cis form, r cis theta form. So r is the radius, right? So this is polar system. Polar system has r theta z. So these are the variables you define the space in polar coordinate system, right? Cartesian x, y, z. So now you can think this r to be this coming from polar system. But anyway, that's the distance. You can take that as radius or displacement or whatever, doesn't really matter, right? In this case, at this point. So now this is a field equation. So both of these are field equations, right? So now we understood what is a field and how do you define a field. So now we will try to understand what is gravitational field. What is gravitational field? Gravitational field is space where the masses are at. So you are dealing with masses in gravitational fields. Masses. So that means you have a field like this. So you have masses, M1, M2, M3. So there are masses, right? M4, like that, masses. So now you might see, I define this mass with a dot, right? So mass is not a dot actually, right? Sun is not a dot. Earth is not a dot. Any object you name is not a dot. But sometimes we define this in a dot and we call it point mass. Point mass. So in point mass, we don't show the volume. We don't show the volume. Right? But the mass is there. Volume is neglected, considered to be zero. Hypothetically, right? Okay. Now, we will discuss about masses and what are the forces between masses, right? So, we call it gravitational force. Gravitational force. Gravitational force. Gravitational force means forces between masses. Forces between masses. Now, these forces are always attractive forces. These forces are always attractive forces. These forces are always attractive forces. They're attracting always. Repulsion is not there. Right? So according to this, suppose you have a mass like this. You have a mass like this here. Now you have distance r. R distance is from center to center. R distance is from center to center. And this mass is going to be m. This mass is going to be simple m. Right? So this is the distance between two masses. Right? So these forces are attractive forces. So there is a force, gravitational force, I would say Fg. And there is another force coming here, and that is called Fg. That is called Fg. Right? So they are attracting forces. You can see the arrows. Arrows are towards each other. So this Fg, we define in this way. So basically, this Fg, gravitational force, is proportional to m and m multiplication, product. This Fg is proportional to 1 divided by r squared. 1 divided by r squared. Right? 1 divided by r squared. This will tell you when r is increasing, your Fg is decreasing. You know that, right? That makes sense when you're going far away. So the force value is reduces, right? So now if you think about connecting these two, you get Fg is proportional to m divided by r square. m divided by r square. Okay. So now how do you make this a equality? You make this an equality by introducing a proportionality constant. So we would say G. Right? G is the constant. So in this case, G is constant. This G is called gravitational constant. Gravitational constant. This is given to you in the exam. Gravitational constant, this is given to you in the exam. So this is called universal constant. What do you mean by universal constant? Anywhere. Anywhere in the universe, this is a constant. Now, there are some constants which is not universal. Means like there is a constant inside this room only. Right? So, but this G is universal constant. This is a universal constant. Right? Okay, so the value of G is this. So you don't have to worry about this. This is available to you in the data book, right? Now let's try to understand about this gravitational force equation. So gravitational force equation, F of G, is G divided by R square. Now, if you think about this mass over here, it is measured by kg, SI units. This is by kg, SI unit. This is by m squared meter in SI unit. This is Newton. This is Newton. Force is calculated by Newton. Force is measured by Newton. You get it? Right? So now, if you want to find the unit of this G, you can isolate G and then you can group all the all other units, and then you can see Newton cross multiply meter squared, then kg minus 2. Agree? Kg squared, you cross multiply kg minus 2. Okay. Now further, so this is one of the unit, right? So SI unit is what you use all the time. So now what is Newton? Also, what is Newton? Newton is coming from F is equal to ma, remember? Newton is coming from F is equal to ma. F is Newton. So Newton is nothing but kg ms minus 2. Agree with me? Newton is kg ms minus 2. Agree? So now I'm going to consider these two. Now when I consider these two, you can see Newton is kg ms minus 2. So Newton is kg ms minus 2. Then m squared kg minus 2. Did you see that? I substitute for it. So now you can simplify this a little bit. M and m square is going to be m3. Kg with kg minus 2 is kg minus 1. S minus 2. That is what you gave me in here. When you Google this, you get this unit. But if you know the details right, the unit doesn't really matter. You can use this one or this one, doesn't really matter. Okay? Now, let's think about this. Let's think about this. I'm going to have a orbit. And I'm going to have a circle, which is, suppose this is Earth. This is Earth, ME. So this is the orbit, right? So how much is the radius here? So we are going to have a mass here. This mass is m is equal to 1 kilogram. I'm going to have a mass here. This mass is equal to m is equal to m. Here, there's a mass. M is equal to m1. Right? So there are 3 masses there. Right? Maybe I'm going to have another mass here. M is equal to again 1 kg. Right? I'm going to have a mass here. M is equal to 2 kg. Okay, that's it. Right. So now we will try to find out the gravitational forces. Okay. Now there is a gravitational force in here. I would say F. I would say F 0. So then there is a force on Earth, F0, right? Those are attractive forces. So the idea is this object is going to attract this one, and this object try to attract this one. So both are attracting, right? Now, let me tell you a funny example. Suppose there is a big elephant. Big elephant, right? There is a small ant. Small ant. Mass M1, mass M2. Now, if you think about gravitational forces, equal force, F and F is acting on each object, right? Right? What can be the observation? If you are here looking at this incident, you can see this ant is going very fast towards the elephant, right? But you can't see the elephant is moving towards the ant. Why? You have to understand the force which is acting on this ant and the uh, elephant is the same. But you can see a huge speed here because of this less mass. Because of this less mass. So if you use F is equal to ma, right? Look, A acceleration is equal to F divided by m, right? If m is less, what would be the acceleration? High acceleration. So that's why you can see as an outsider, the ant is going really fast towards the elephant. But physically, you can see the same force is acting on this. Okay. So now the same thing I'm explaining here, F0, F0. You understand? Now, if you take another one here, this M mass, right? So you have a force here. I would say Fm. And I'm going to have a force here, which is going to be Fm again. And what about this here? You have Fm1. What about this? Same thing, Fm1. Then what about this here? What about this here? Is going to be Fm, I would say F2 or something. It's going to be F2 or something. Then from here, I'm going to say this is F1. And here you will see F1. Okay. Now you will see this force, or actually this is going to be F0, okay? F0. Because you can see this F0 force equal to this F0 force. Correct? Other forces are totally different. Other forces are totally different. See? These forces are totally different. Three different. Right? Now, look at the calculation here. F0, I'm going to find. Look at the calculation. F0, I'm going to find. F0 is equal to G mm. So it's going to be me multiplied by 1 divided by r square. So which is essentially GME divided by r square. Now, if you really look into this, I'm going to define this in this way. This is nothing but gravitational force for unit mass. Gravitational force per unit mass. Do you agree? Gravitational force per unit mass. Why unit mass? Because you can see m is equal to 1 kilogram is used. Correct? So we will give a name to this one. We will give a name to this one. Simple G. We will say simple G is the gravitational force per unit mass. Okay? Now, if that is the case, this F0 also G, isn't it? This F0 also G, isn't it? So that is gravitational force per unit mass, right? So we know math, right? So we will try to play with it now. Now, this force, can you understand? This force is 2 times of F0. Why? Because 2 kilogram is used here. In the previous one, 1 kilogram. So you understand this is nothing but now 2G. You understand? Yeah. So going through that, we will write this one to be 2 times G. Now we are writing that in terms of the F0 essentially, which is G. Okay. Now if you go into Fm, then here, what is that? M, G, and what about this one? M1G. Now you should see the connection. What is the connection? What is the connection? Connection is this, my friend. Now, in earlier lessons, we saw that this is ground. Suppose an object is falling. This object, mass m, falling. When it is falling, we talk about the force, right? Weight, we call it weight. What was that? M, G. mg, we call it weight. Now, with this knowledge, you have to connect this with this. Now, the whole point of VC is the depth. Now, when you see the relation between these two, then you have to understand the relation between these two. Because simple G is that, right? When you have the connection between that, you have to understand the connection between these two, which is this, right? That's the whole point here. So now we call G, mg, weight is mg all the time, right? Now what is this G then? We call gravitational acceleration, right? We call gravitational acceleration. Now, it appears to be this gravitational acceleration is nothing but this, right? That's the new thing you learned today. The new thing you learned today, gravitational acceleration is nothing but gm Earth divided by r squared. Right? So this you can say gravitational acceleration, or you can say gravitational force per unit mass, gravitational force per unit mass, or you can say gravitational field intensity. We call it gravitational field intensity, gravitational field intensity. Right? So now G is gravitational acceleration, gravitational force per unit mass, gravitational field intensity, G. Now we'll go deep, little deep. You go to that gravitational field intensity, which is G. So this guy is nothing but G now. That guy is nothing but G, right? So accordingly, we have mg, m1g, 2g, and all those things, right? Let's try to think about G now. This G is gme divided by r square. Now you will understand these two are constants. These two are constants. So from here, you will understand this G is proportional to 1 divided by r square. G is proportional to 1 divided by r square. So that will tell you that this G is a function of r, isn't it? G is a function of r. So when r is increasing, what will happen? G is decreasing, right? Yeah. So let's try to visualize this more. Let's try to visualize this more. So I'm going to have a orbit. I'm going to have an orbit just around the Earth surface. Just around the surface, like the dotted one, right? And I'm going to have another orbit little away. Little away. And I'm going to have another orbit here. And I'm going to have another orbit here. Now, let's think about the distance. So from here to here is RE. RE means Earth radius. Earth radius. I'm going to get this distance, this height. I'm going to get this height to be what? I'm going to get this height to be, suppose, 100 meters. 100 meters. So that means a building. So there is a building. This is a building. Building. Right? Now, from here to here, R1, and from here to here, R2, and they are very big numbers. Very big numbers. Right? So, I'm talking about G in here. What is the G in here? G m divided by RE squared. Right? Look at the board first. Understand. I'm going to get this orbit, and I'm going to say that is G1, and that is Gm divided by RE plus 100 squared. Agree? What about this one? This one is G2, Gm divided by R1 square This one is Gm divided by R2 squared, and that is G3. Agree? Now tell me RE. What we know about RE? Earth radius. How much is the Earth radius? Earth radius is 6,400 kilometers. Very big. Earth radius is 6,400 kilometers. Convert that into meters. That would be 6,400 10 to the power 3 meters, isn't it? Right? So now this is nothing but now 6.4 times 10 to the power 6 meters, right? Very big. Very big. All good? Now you have to think about this. Think about this. RE plus 100. 100 is the 100 meter, the height of the building. RE is 6.4 times 10 to the power 6. So that plus 100. That means that 100 is negligible. So because of that, we write this one is similar to G. Right? Okay. Now, this G value is 9.81, what we use all the time. So this value also 9.81 then. Right? So now if you think about G2, now you understand when R is increasing, G value is decreasing. When R is increasing, G value is decreasing. Right? So G2 value, you understand, G2 value should be less than 9.81, right? And then this G3 value is even smaller than G2, right? So we have to understand this 9.81 number can be used around the Earth's surface only. See, around the Earth's surface, here, see, it's 9.81. But when you go further, see, they're different. When you go further, they're different, right? So this is the message now. The message is gravitational field intensity is G. That value is 9.81. That value is 9.81 around the Earth's surface. When you are going away from the surface, G value decreases, right? Yeah. So that is the summary.